hardware. The robot is called an EDDI. It's by Parallax. EDDI stands for Expandable Development Disks for Innovation and Experimentation. And Microsoft came up with a standard for their Microsoft Robotics Studio called MARC, which is Mobile Autonomous Robot with Kinect. And they basically said if you build to this standard, it will work with Microsoft Robotics Studio. So Parallax did just that. I'm going to go through the standard features real fast, and then I'm going to talk about the extras that I added. So we have two 12-volt motors. They're geared motors, pneumatic wheels on them, and they have wheel encoders for wheel position and speed. A couple of 7-amp-hour gel cell batteries on the bottom. On the main deck is the heart of the robot, is a control board with a propeller chip on it. Now the propeller chip is made by Parallax. It has 8 cores that they call cogs that are running 20 million instructions each cog, so which means you have a total of 160 million instructions per second running on the control board on the EDDI. You also have a set of sensors right here. Now there are 3 infrared sensors and 2 ultrasonic or ping sensors. These are basically distance sensors. They have 2 types because some objects reflect sound better and other materials reflect infrared better. So that way this gives a complete view of the environment. On top here we have the main platform where the laptop runs. Now Robotics Studio is a little different than a lot of robotics platforms out there in the fact that your logic actually runs on the laptop. The laptop then sends commands down to the control board like drive the motors, drive forward, rotate in a circle. It can also send down a command asking for sensor data, and the control board is in charge of gathering the data from the sensors and then sending it back up to the program running on the laptop. So that's a little different than a lot of the platforms out there. Now that could be done wirelessly like with the Zigbee, except for one thing which I'll hit in a second. So we'll go up to the top here, and on the top is the Microsoft Kinect itself. Kind of an amazing device. It has a scanning infrared laser and something called a depth camera, and that's what allows it to see in 3 dimensions and to extract the skeletons. It also has an RGB camera, and an amazing thing that very few people talk about it's got an array of microphones. There's 4 microphones along the bottom, and these are used for speech recognition. They're also used to determine the direction of the sound. So I use that in my help application. When somebody cries for help, the EDDI can find them by localizing their sound. This is also the reason why the laptop has to sit on the platform itself, because it generates a lot of data. It uses 61% of a USB 2.0 bandwidth, so that's why the laptop is on the platform. Now working down, there is a camera on here, but the version of software I was working with, you did not have a webcam interface, so I put a Microsoft high-def camera here for the televideo conferencing. I also added a photoresistor, and this goes down to the control board and uses one of the available pins on the A to D converter, and this can tell whether it's light or dark, and I'll show you why in a second. So going on down, EDDI talks, and so I have some USB powered speakers down here to make his voice a little louder. I also have a USB hub because lots of things going on USB and I needed additional ports. And then I also added this, which will turn on. There are 3 auxiliary ports on the control board that will switch 12 volts at a fairly high current. I use that for 3 LEDs. The blue LEDs are activated whenever EDDI moves, just to give better visibility for seniors to try and avoid a tripping hazard. The red LEDs, if EDDI is coming along and something gets in front of him, like a family pet or a senior, he stops, he turns on his red LEDs once again, signaling for a tripping hazard. If he's in the search and rescue mode, if somebody has cried for help and he's looking for them, he checks the photoresistor to see how dark it is, and if it's dark, he then turns on the headlight so that they have a little better picture from the camera when the caregivers call in, televideo conference in, to talk to the senior to give them assurance that rescue personnel are on their way. So anyway, that's a quick rundown of the hardware.
When When I started this project, I had worked with the Parallax propeller chip, which is the control board for the eddy. However, I was not a C# programmer, a Kinect programmer, or an RDS programmer. So out of necessity, the Visual Programming Language, or VPL, environment was my primary developing tool. VPL is a visual programming environment that simplifies the design and implementation of the message passing environment of RDS4. VPL provides a workspace for program development and two groups of resources known as base activities, right up here, which are things like data, variables, flow control, like if statements, and a category known as services. Now, services can be as simple as dialog boxes or as complex as the entire interface to the robot. For example, the interface for eddy is under the general category of mark, and you can simply type it in. It does a search for it, and the mark robot comes up. Now, the mark robot as a basic service was okay, but I had a lot more code that I needed to write in this environment that interacted with that. So up here in the basic activities, there is a neat feature called activity. And basically you select it and drag it into the workspace, and then it becomes a service essentially unto itself. You can double click it, and that opens it up, and you have a brand new workspace. Now you also have you can have a series of tabs that are all part of this same basic activity. So essentially you just use it like any other VPL workspace. You take things and drag them in. And I missed that one. There, we'll grab a calculate, and then connect them with a message flow line, and you proceed to generate your code. Now, the neat thing about this is that once you have this built up, you can go up here to build and decide to compile this as a service. Now, when you compile it as a service, it creates C# code and then compiles it and drops it down here into the services category. So this does two things. Number one, it runs quite a bit faster, but also it encapsulates all this code and reduces the complexity of your program. Now, you can see here, this is part of my help coding, and right in this area here you see new TLC mark, and these are services that I generated by creating activities using the mark robot interface inside of them and then wrapping code around them, and so it greatly reduced the complexity of this drawing. This would be really a mess if I had not done that. So anyway, that's a really neat feature. Now, when I under the services, we also have Kinect, because that's a major part of the project, and there's the Kinect service. But after working with that a little bit, I realized that I couldn't add the functionality to it that I needed for the project, so I could not use it as the basis for an activity that I built. So that led me to C# programming. C# programming, you use Visual Studio, and you use a standard template that they have for Robotics Studio, and it helps you build a service based on CCR and DSS, decentralized software services, and coordination and concurrency runtime. Boy, took a second. So you see, we have the Kinect, but we also have Kinect tracking with pose, and the Kinect tracking with pose is the activity that I built, the service that I built using C#. So anyway, it's a really nice environment. I discovered that creating my Kinect service directly as a CCR DSS service presented challenges in rapid design, feedback, and debugging. To solve this, I created a simple tool in WPF that I used to understand the Kinect and to develop my service. The top row shows the tracking state as well as the skeleton number. The second row shows the X, Y, and Z coordinates of the center of body mass, which I use for tracking. My project required position recognition, which I accomplished by using a 3-point angle system of the major joints. By watching this display and assuming different positions, I was able to establish a range of angles that could differentiate poses. Because this is monitoring a person rather than being used as a game input device, I discovered that I had to split right and left joints to compensate for movement. The help portion of my project utilizes both speech recognition and beam angle, which are shown in the bottom two entries. After the recognizer hears the cry for help, it then uses beam angle to locate the source of the sound and find the fallen individual.